Hi guys, this is GK from GK Marine Tech. Today lesson we will discuss about inductive load behavior in AC system. Okay, this is very important to understand the power factor. So this today's lesson is we are going to discuss about inductive load and capacitive load. What is the behavior in the AC system, not in the DC system. So we are not going to discuss the DC system. Okay, so before entering into the discussion, we will just refresh the basic laws, Faraday's law and next one is the Lenz's law. Okay, this both are very important for understanding the principle of induction motors. Okay, the Faraday's law, what it says, if any inductor like this coil, this is the inductor sample I took, so any inductor and near the inductor, if you move the permanent magnet, okay, or you keep the permanent magnet and move the inductor coil near the magnet, whatever it is, the relative motion should be there. So wherever the relative motion between coil and magnet which is nearby, then one EMF will be induced in the coil. This everybody knows. Okay, so from the magnet generator, the magnet they are making rotation so that inductive coil EMF voltage is producing and that voltage is the generator output. This is a basic principle. It is not a big theory in this. But why I want to refresh this in few seconds. You will understand why I am saying this. Okay. So if you are doing this one, what is happening? You see, the magnet is moving. Up to that, there is no change in the flux. If no change in the flux, there is no movement. There is no voltage. But if the change in the flux, because of this flux is happen, because of this magnet, it is going close to the inductor coil and it is cutting the inductor lines. Okay, this magnetic flux, this is a permanent magnetic flux, this flux is cutting the inductor. If you cut the inductor, you will get the EMF voltage. Okay, so this is the Faraday's law says. Faraday's law says what? If any movement in the magnet near the induction coil, that induction coil will get induced EMF. That EMF we can use as a supply, electricity supply. Okay. So, but now the theory, the Lenz's law theory, what they say, initially Faraday's law only they invented, but after that Lenz's law states there is a direction of see, if you are going closer, here EMF is induced. Not only that, here also one more magnetic flux is creating. Correct? Around this also magnetic flux is creating because this EMF is we are using. The EMF we are using for the load. So there is a current change in the inductor coil. It will make a magnet. If any current change in the inductor coil, it will create a magnetic flux. Its own flux. This flux is different. Actually, this permanent magnet is having a permanent flux. But this flux, because of this EMF induced in the coil, that EMF is cutting the, because of changing the flux, it is again, see, again it is cutting the coil. So, it is producing EMF, that EMF is producing one more magnetic field. Okay. So, Faraday didn't think about this, only he said if any movement is there, relative movement is there, EMF will induce. But Lenz said that because of this action, there will be another magnet is creating inside the coil. For that magnet is also having a direction. Faraday didn't say the direction of the magnetic flux is producing in the coil. But Lenz said it is having a direction, but the direction is not favored to this magnet, it is opposing. We will see how it is opposing. This is very important. You see, now I shown the magnetic direction. Before I didn't show the magnetic direction, just the flux is coming and going away. So now I shown that direction, but clearly you monitor that. See, when it is coming closer, north and north is coming closer. That means due to Lenz's law, the direction of the magnet is opposing this magnet which is producing actually. This is the magnet is going to produce the EMF. So it is opposing this nature. So this is a loss for us. This one only Lenz's law states. So whatever the magnetic field creating here, that magnetic field is cutting against the coil. Okay, EMF is induced, but the magnetic field cutting the coil again. Due to that, there is one more magnetic field is induced, back EMF they actually. This magnetic field will be opposed to the magnet. This is Lenz's law states. Because of this only, this is the basic problem or maybe disadvantage will create the power factor. Reactive power we used to call. Next lesson we will talk about a little more detail. Okay. So Faraday's law said if any relative movement between the magnet and the inductor, you will get the EMF. Lenz's law said if during the production of EMF, the magnet flux will produce and it is having a direction and the direction is opposing the main magnet. Okay. So this one you have to understand. Okay. Now we will go to the next. This only for refreshment. Okay. This practically also we can check this. Okay. Now we will think about three loads: resistive load, capacitive load, and inductive load. We heard about it. First we will talk about the resistive load. Resistive load, I took one AC source and I given to the load. I'm not giving a two circuit and all. Just for understanding, I make it is like one conductor and current is passing through. I am not connecting the conductor directly. I am making the restriction here. Making a restriction here, that is called resistance. So resistance means some restriction which is resist the electron flow or current flow. That is called resistor. Already we saw. So this restriction, what will happen? The amount of electron or amount of the current passing through this, it will reduce after the restriction. Correct? So if you are supplying, see now I am supplying the current, but it is going very less current and the light is flowing according to the resistance, the delay. But there is no delay in the current passing. There is no delay in the current passing. Only less amount of current is passing, that's all. But there is no delay, no time delay. If you switch on, immediately the bulb will glow according, depends on the resistance. There is no delay. So this is in phase. We used to call in phase. Current sine wave and voltage sine wave will be in the same phase. This is the one last lesson we discussed. Okay. So now I am going to change resistive load. Not much thing to learn, but just for understanding I put it. But now we will go to the inductive load. Very important load to the AC circuit, because the inductive load will behave very much funny, and then depends on that a lot of disadvantages that we have to overcome that. So inductive load, instead of resistance, I change like this turbine. Turbine is a heavy mass, it is that. So if you rotate the turbine, then only the electron will flow. Initially electron will not flow here, it will run the turbine. This for understanding I am saying. Don't think that we are inductor inside there is a turbine. Just for easy understanding, I told this conductor is having one turbine inside in between. Okay. Now what I am doing, I am going to supply the current. The current will not immediately supply. The current means voltage is ready. Okay. So voltage is supplied. There is no delay in the voltage, but the voltage and current, the current will not pass through this. What it will do? What it is doing? It is turning this wheel first, then it is allowing the current. If it is a AC, so the current is going forward and reverse, forward and reverse. That is why it is turning different direction. But always the delay. Delay means what? Current movement delay, not the voltage movement delay. So voltage you are giving in the proper time. Voltage we are not changing. But the current, it is delaying because of this reason. This turbine reason. So always the voltage sine wave and current sine wave will not be in the same line, same phase. It will be delay. Which is delay? Current is delay, not the voltage. Voltage is present. I told you without current also voltage will be there. So voltage will not change. You cannot delay the voltage. So voltage you are giving, but current, it will not follow the same sine wave path. It will delay. Okay. And after stopping also depends on the momentum, the running momentum, it will move some more current after stopping bringing the voltage to zero. Sine wave I told you one cycle 2 times, the sine wave will become 0. So if it is become 0 also, because of this wheel is turning little more time due to the momentum, the current will go. The light will glow after become voltage 0 also. That is why the current wave is little lagging. That is called lagging. If it is delay the current curve, that is a lagging. Okay. So this is the inductive load principle. So because of this lagging, what is going to happen? Because of lagging, some of the power it is going to waste. Worthless power you used to call, or waste power, or reactive power. So that power we have to compensate in the generation. That ratio, amount of waste, that is called power factor. Okay. So this is the inductive load behavior in the AC circuit. Okay. Now capacitive. Capacitive is not a load. I will tell you. First you understand capacitive action, what is that. Then you will realize capacitive is not a load. Capacitive we are using to improve this loss. This delay in the current, we have to improve that. For that capacitive we are using. But only capacitor will not behave like a load. Inductor will behave like a load. Induction motor is a load. Instead of, in place of induction motor, you remove the motor and put the capacitor there. That is not a load. Capacitor is only one component which we are using for improving the power factor. Okay. So we will, that is why I mentioned capacitive effect. Capacitive effect. Capacitive load is not a capacitive load. It is a capacity effect. So you can understand this principle the similar way the capacitor is going to act. Capacitor is having two terminals. In between, one electrolytic partition will be there. Correct? So electrolytic partition will not pass through this isolation part. So the current will not pass through this partition to the other side. That means what? Current will not pass through the capacitor. But in AC, current will allow. That's what the theory says. How the AC current is allowed? Current, how it is allowed, we will see now. That actually current is not allowed. Whatever the action in the current movement here, this movement is transferred there through this partition. You got it? Before inductor, the current itself, after running the turbine, it is passing through and it is reaching the load. But here, whatever you are supplying the current, it will be go up to the capacitor. After capacitor, this movement only transferred, but this current is not transferred there. I think you are getting confused, but you are, in few seconds you will understand what I am trying to say. See, now I am going to supply the current here. Now the no current is there, that is why it is in the center. Now I am going to supply the current. So what will happen? This both side spring is there. So it is pushing the spring and bulb is glowing. But after pushing time, it is pushing up to that, the movement of the partition, there was a current movement. Got it? From center to left side, the partition is moving because of this current coming. So this, due to this movement, there is some movement in the current. That current, due to that current, the bulb was glowing. Now again I will put it this side. Okay, AC always it will go this side and this side. No. Now I am going to remove the current. Okay, this side current I am going to reduce. So what is going to happen? You see, I am going to reduce here. The partition going to come here. That time there is a current movement from here to this capacitor. See, that time also bulb is glowing. But after reaching here, there is no movement. Movement is stopped. So capacitor, through capacitor AC will pass, but up to some time only. Within the time you have to change the polarity, so you can continue this movement here. Here whatever the movement is here, see whatever the movement is here, bulb is glowing. After bulb, before bulb stop, again move it here, again bulb is glowing. This is fast, 50 cycles, it is going movement here. This same movement is transferred there. You got? Now you understand. So if you are supplying the DC, what will happen? It will, all the current will go and it is pressing this partition to the maximum in the one side. Up to moving, there will be some current. After that, there is no current movement and the load will not go. And voltage also will not be there. So capacitor will not allow DC, it will allow AC because of the AC is going forward and reverse, the same pattern. The other side of the capacitor also forward and reverse it will move, so that we are getting the same effect. Now you got the idea. But now when it is coming back, it is not pulling, actually because of the spring action it is coming out. So it is assisting the current movement, correct? It is assisting the current movement. That is why this will support the current movement. In AC circuit, this spring action will support the current movement. It will lead instead of lagging. Inductive load, what it's done? It delay the current movement. This will advance the current movement. It is opposite of the inductive behavior. Capacitor is the opposite effect of inductive behavior. That is why wherever the inductive load if you are using, if it is you have a too much delay in the current, you can use the capacitor to make it advance. Now you got, I think you got that idea. The capacitor is for improving the time delay, of the current in inductive load. So wherever the inductive load is too much, we have to use the capacitive bank for improving, power factor improver they used to call. Two ways we can improve the power factor, that in power factor class we will discuss. One is by capacitor bank, another one synchronous motor. We will discuss about also future shaft generator, how it is working. In that we are using that synchronous motor for improving the power factor, because shaft generator very low RPM, they are developing the power supply. So for that power factor improver is must. Okay. Even now you got idea. So after, if I stop here, it will become equal. Slowly the capacitor will become equal both sides and it will be staying in the center. When you are starting, it will capacitor will work. So now you can understand why I am not saying it is a load. It is not a load, because if you put it DC, it is not keep on bulb glowing. Bulb is getting off. Only about few seconds it is not passing the current. It is making the current movement in the other side. Okay. So now you understand difference between the inductive load and capacitive load. This is very, very important, basic. If you don't understand, again you watch my video from the beginning, so you will get it. Because if any confusion in this understanding, up to end, I am telling you, up to end, you will get always confusion. You will think about capacitor is like a battery and it is storing energy and releasing energy whenever required. That is also purpose, but in AC circuit that is not a purpose. That is only for the DC circuit. Okay. AC circuit, the capacitor acting for different purpose. So if you, definitely some motor is having a capacitor. So with the capacitor value, this movement spring is become weak or something, electrolyte is leaked. So you have to understand, without this capacitor or weak capacitor, what will happen in the load? That is why I told the basic principle is very, very must. We are missing this basic principle because we are getting bored and everybody wants to work practically. Fault finding, troubleshooting, they want to repair, they want to run the machinery. But that is not directly, you cannot go on attempt. If you understand this one, after that any machinery, any kind of machinery, if you open it, you see the circuit or how the system is there, you will easily can troubleshoot. You can make your way of troubleshooting special, particular that you can, then you can find the fault easily. Okay. Now we will see what is the effect in the curve. I will show in the curve. Now I told it will be advanced and it will be lagging, delay. That one we will see in the curve. So this is the resistive load. Resistive load already we saw. This is a volt curve. The orange line, the yellow line is the current curve. Current will vary, depends on the load. Okay. Voltage we are giving. Voltage will be there. Generator, how much voltage is producing? 440 means 440 voltage is there. But the current is depends on the load. Two motors running, there will be current more. If one motor running, current will be less. Current will vary, depends on the motor. Now we are not thinking about the amplitude of the current. We are going to talk about the timing difference. Now you see, if voltage is become 0, then the current is also 0. Again in negative direction, voltage comes to 0, current also comes to 0. There is no delay. So this section, both voltage and current 0, this section voltage and current 0, right? So we can mark it that one. Here also voltage also 0, current also 0. Okay, here also voltage is 0, current also 0. Got it? Now inductive load, how it is coming? This one phase. So the difference between this current angle, you see here, difference between the point crossing the 0 line, difference between the point where the current and voltage curve is passing through the 0 line, the distance is actually, I told you, time we are calling it as a degree, 360 degree, right? So this degree difference is 0 because it is in phase. It is in phase, current in phase. Okay, current is in phase because voltage and current is the same phase. There is no difference in the degree. There is a difference in the amplitude, that is depends on your load. Got it? Now inductive load, what is happening? See, the current curve delayed because here the voltage started from this center point, but it is reaching up to here, then only current is started rising. After that the voltages become 0 here, but the current still there, the same position, current is still there, and current is 0, that time voltage is in the reverse direction. This is very important, and due to these actions, see, the current curve is lagging. You can see here where it is crossing the 0 line, voltage curve is here and current curve is crossing here. There is a delay in the current. Voltage we are not thinking about, voltage we are giving in steady. Current only it will delay or it will advance. So what will happen? If you see the phase difference, this is the phase difference. How much difference? This is one cycle, I told you 360 degree. So we can check the distance. So how much degree difference? That is phase angle. Phase difference actually. This phase angle, if you take it cos phi, cos phase angle, cosine of phase angle, that is called power factor. Power factor is the value as a ratio of waste energy, how much energy you are going to utilize in the generator supply. We will talk about detail in the next topic. Okay, so this is the inductive load principle. Current is lagging. Now current is lagging. So if any current, any electricity you are telling lagging or leading, that is a current only, not the voltage. Voltage will be the reference, and current you have to check whether it is lagging, either delaying or advancing. This is lagging means delay. So this normally inductive load 100% it will lag. Pure inductive load it will lag 90 degree. It will lag from up to center here. Up to here in pure inductive load, it will start from here. But definitely we will not supply the pure inductive load, it is having a resistance and other things also. So it will, you will get some phase difference, phase angle difference, that is called cos phi. We have to reduce as much as possible. Definitely you cannot reduce to 1. 1 is the unity power factor. You cannot reduce the, advance the current and make it 1. Make it 1 is very, very difficult. It's not possible. But make it 0.9 to 0.95 is good. Good power factor 0.9 to 0.95. 0.85 poor power factor. We have to improve. Okay. Or we have to have some other arrangement to take care of this power factor to adjust it. Okay. Now you got the idea of inductive load, what is the effect in the sine curves. Okay. And now we will talk about the capacitive effect. I told you effect, it is not a load. Okay. Capacitive effect, you see, the current is leading, advance. Before supply to the voltage, there is a current movement. Before giving the voltage, there is a current movement, and here is it is crossing the 0 line. There we are taking the phase angle. So phase angle now will be leading direction. So this time you will tell current leading. So now you understand leading means what, lagging means what, why it is happening. And capacitor is not a load, it is used for improving the power factor. Inductive will delay the current. I told you, due to the Lenz law effect, the current is opposing to the cause producing it. That is why it is delaying the current. So due to the delay current, there is a lagging. Current lagging is there. Time delay is there. For adjusting that one, we can use this capacitor so that this will compensate that lag delay. It will compensate the delay so that you will get it a better power factor. Okay? So this is the thing we have to be understand before enter the topic power factor. Because power factor, it is a simple only, but you have to know about the inductive effect in the AC circuit. Okay. Now the now I told you, inductor, we have a 3 component. Normally RLC, maybe heard about it. Inductive motor, we have a 3 component: resistor, inductor, capacitor. So these 3, resistance is a resistance. We will see resistance is a resistance. It is unit is ohms. So resistance, what is the duty of resistance? It is restrict the current movement. Depends on the value, it will restrict. It is nothing different. Resistance is very simple. There is no time lagging, there is no time leading, no lagging, no leading. Current lagging is not there in the resistance in phase unity power factor. Okay. But without resistance, there is no load. Even inductive load is having some resistance. So resistance always will be there. But inductive load depends which one you are using. You are using the magnetic energy, then definitely inductive load will be there. Okay. So inductive load, inductor, if you take it, I told you in DC, inductor is just like a conductor. There is no effect of the inductor in DC circuits. But we are not talking about the DC circuits. We are talking about the AC. AC, as per the Lenz law, I told you it is opposing the power supply. Correct? It is opposing the power supply current, so that the current is lagging. So definitely the inductor is a AC resistance. You can call it as AC resistance. The name of AC resistance is reactance. We cannot call it as a resistance. Resistance means it should be same in AC circuit and DC circuit. Resistance means it is a resistance behavior in AC and DC. But this inductor, AC circuit is behavior resistance and DC circuit is behave like a good conductor. And that means zero resistance. Correct? It is not behaving in the same manner. AC, it is act as a resistance. DC, it act as a zero resistance. There is no resistance. So we are calling, we have to name difference. Now we shouldn't call it as a resistance. So we are calling is AC resistance in terms reactance. It's called reactance. Because it is reacting, no? The magnetic field we are producing for making a EMF, that again it is producing back EMF and it is opposing the supply. That is why it is called reactance. Capacitor also same purpose, but this is delaying the current, this is advancing the current timing. So both are called reactance. But we have to make it some different letter. Okay. So reactance means X. X is called reactance. But the reactance is due to inductor, then it is called XL. If the reactance is due to capacitor, we used to call XC, capital XC. So R is that ohm resistance, XL is the reactance of inductor reactance, and XC is the capacitive reactance. All in only AC circuit. Don't apply for the DC system. AC system only we have to apply for this term. DC system there is no term. It is an inductor, it is a conductor. We don't bother about it. Okay. Now how to find this? Because this here there is a value. Multimeter you can check. But these two resistance you cannot check in the multimeter. Multimeter you can check how much the value of the inductor value is Henry. Inductor value is Henry. The unit is Henry. And capacitor value is Farad. Capacitor value is Farad. This is ohms. Resistance is ohms. Okay. This Henry nowadays our multimeter can measure this Henry, how much this inductor coil, this is depends on the shape and coil thickness, inductor thickness and the size of the winding and all, number of turns all make difference in the Henry. Capacitor is, you know that, two plates will be there, in between electrolytic solution will be there, so it will act as a capacitor. This is called Farad, this is called Henry. Only if you select the Henry, you will get some inductor. You will select the Farad, you will get the capacitor. But this is not a resistance. This is the value of this inductor. This is the value of this capacitor. Okay. So from this unit, you have to find the resistance, that is called reactance. So from Henry and Farad, how to calculate the reactance? There is a formula for inductor. Formula is 2 pi FL. 2 pi FL. 2 pi, you know the value. Pi is 3.14 and 2 is a constant, and F is the frequency. F is the frequency. Our frequency is 50 Hertz. This L is the Henry. L is the Henry. You have to be very careful. That should be in Henry, not in the smaller unit or bigger unit. It should be in Henry. So if you multiply this one, you will get XL. You will get XL. So now you see inductor Henry will not change, but the frequency is very, very important. Our 50 cycle frequency shift to 60. Okay, 50 cycle frequency, this reactance will vary. If you increase the frequency to 100, then the reactance will increase. Okay, so it is directly proportional to the frequency. So inductor reactance is directly proportional to the frequency. But we are not going to change the frequency, so we don't bother about that. We will think about that inductor is having some AC resistance, like that capacitive. Capacitive resistance we used to call as a Farad, and the formula is 1 by 2 pi Fc. 1 by 2 pi Fc. So the F is coming in the denominator and C is the Farad. C is the Farad. This is very, very important. You should not put microfarad. You should not put microfarad. If it is microfarad, you have to convert into farad, then you put the value. Otherwise, you will not get the answer. Okay. Now, 1 by 2 pi Fc. This is all in denominator. So it is inversely proportional to the frequency. This is directly proportional to the frequency. This is inversely proportional to the frequency. So if you take one inductive load, or it is having three loads, capacitive, inductive, resistance, all three loads in the circuit, you have to calculate the total resistance. You have to calculate the total resistance due to reactance of inductor, due to reactance of capacitor. All three you have to calculate. You have to add together, but you cannot add directly. You have to add phasor method. You cannot add directly because the phase direction is different. Phase direction is different. So how to add? So we will see how to add. First we found all three is important. Then I will tell you how to add. Take one resistance, one inductor, one capacitance in series. So series circuit, how to add? If you add all three, the value is not a resistance, it is not a reactance, right? It is a total resistance of inductor, capacitor and resistance. It is called impedance. It is called impedance. The letter denote is Z. Letter denote is Z. Z is impedance. Because these words again and again your field you are going to use. Impedance, resistance, reactance, kVAR, kVA, kilowatt. This confusion always will be there. That is why I am explaining. So impedance means it is a combination of resistance, inductive resistance and capacitive resistance. Okay, capacitive is not there, only inductive resistance and resistance. Whichever the resistance in the line, all together if you add it, the total resistance will be impedance. So you have to take it as a calculation for impedance only, not only resistance, not only inductance, reactance. Okay. So how to add it? Because the resistance is linear. This is all 90-degree direction difference is there. This is 180-degree difference is there in this. So this is the method of adding. I don't want to explain how the formula is coming, but this is the formula. Impedance equal to R square. R is the resistance value. okay, ohm square plus inside the bracket the difference. Inductive reactance will be always in the front, inductive reactance minus Xc, capacitive reactance. If it is capacitive reactance 0, you can put it 0, only inductive reactance you can take. Or inductive reactance 0, then you can use only the capacitive reactance. But whatever it is, final answer will become square, that will become in the positive value only. Even it is a minus. Suppose this Xc is more, XL is less, but because of the square, you will get positive value only. So don't think about it. You have to make the difference. XL minus Xc. The difference you have to square it up, then add together, then final value take a square root. The final answer is the impedance. This impedance only you have to use for the Ohm's law, power calculation or voltage calculation or total current calculation. If you want to find the V equal to IR, I told you. So in that we are putting the R, no? That R now you have to put Z for inductive load. Now we got the idea why we are calculating all those things. This is a very important basic topics. It may be bore, but it is very important. You take a note of it so that future time, if I am explaining or talking about impedance, talking about the reactance, then you will not get confused. What is the reactance? You will not ask, because you should know about this. Now I think this lesson we are very much clear about the inductor behavior, capacitive behavior and resistance behavior. What is lagging, leading, what is the effect, what is the Faraday's law, what is Lenz's law, everything we talked. Next chapter, because of due to this effect, I told you the power factor will come. So what is the power factor, how to calculate, what is the relation between kVAR, kVA, kilowatt. This is a very important, because transformer, if you take it kVA, they will mention kVA, and reactive kVAR, sometimes kVAR load also meter is there. In ship you maybe see that kVAR meter, kilowatt meter or kVA meter. So what is the difference? All is not same, different. So we will discuss about in the next lesson. So I hope next lesson we will complete the basic theory, then we will go to the practical, like a machinery, one induction motor, how it is running, like a generator, how it is producing the electricity, what is in the generators. So everything we will discuss one by one. So one more class we have to follow for that power factor. That is a very important thing. After completion the power factor, we will go to the AC induction motor, how it is running. DC I am not going to touch, but AC induction motor I will tell you how it is running. Then I will tell that generator, how it is producing electricity, how we are taking care of the power factor, what is in the generators, everything one by one. We will go with the good animations, 3D animations. So we will catch up in the next video, next lesson. Thanks for watching.